Welcome to my 3-unit investigation on an object in motion. I will be analyzing the motion of this ball as I kick it through the air until it reaches the same horizontal starting point. By using this app called Tracker, I can follow the movement of the ball frame by frame and use my own height of 1.62 meters as a scale. The app will automatically interpret the data in terms of displacement, velocity, and acceleration in the horizontal and vertical directions. By using the supplied axis tool, I observed that the initial angle at which the ball was launched was 77 degrees to the horizontal. Now to derive the equations of motion. We know that acceleration in the horizontal direction is always zero, due to Galileo's analysis of the independence of vertical and horizontal motions of an object. So we can start with acceleration of x equals 0. Integrating that, we get to velocity of x equals some constant. There are two ways we could get this constant. We could use the table of values that Tracker gives us from its frame-by-frame analysis of specifically the velocity in the x direction, or we could use the cos function with initial magnitude of velocity, which was also supplied by Tracker. The app gives the initial velocity of the ball as 10.62 meters per second, and using the angle 77 degrees, we get horizontal velocity equal to be 2.3 meters per second. However, because the table of values is more specific for what we want, and more reliable in terms of data, I chose to get the average, which ended up being 2.6 meters per second. To get the function of displacement in the horizontal direction, I integrate again, giving me a final equation of x equals 2.6 t. This was because I chose the starting point of the ball's flight to be at the origin, not shifted forward or backward at all. Now to move on to the vertical equations of motion. Due to Galileo's observation of gravity, it is always a constant value. However, in order to find this, we can't just go with 9.8 or 10 meters per second squared. Because of air resistance and the uneven field and the unreliability of the phone's camera, I decided to use a table of values for vertical acceleration that Tracker gave me, and take the average, which ended up being negative 10.5. I integrate this to get the function of vertical velocity. However, I can either use initial vertical velocity that Tracker gives me, or I can use the sine theta method like before. Tracker gives me an initial vertical velocity of 9.826, while multiplying 10.6 by sine 77 degrees gives me 10. Because both values are reliable, I decide to take the average of both, which ends up being 9.9 for initial vertical velocity. Continuing the substitution for c, I end up getting negative 10.5t plus 9.9 for my vertical velocity. Integrating again to get vertical displacement, I get negative 5.25t squared plus 9.9t plus a constant. However, because I kicked the ball from the origin, the starting points both horizontally and vertically end up being 0, which means I get a final equation of y equals negative 5.25t squared plus 9.9t. I graphed these equations separately, all as functions of time, on Desmos, so I could compare them to the automatically generated graphs that Tracker gives me. Here are the two graphs of vertical displacement. Tracker gives the time of flight to end at 1.9 seconds, which is when the ball comes back down to 0. The equation I derived gave the time of flight to be 1.886, which is extremely close. Half of this time is at about 0.95 seconds, which will be when the object is at the peak of its motion. Tracker gives the height of this time as 4.67 meters, whereas subbing it into the equation on Desmos gives y equals 4.66 meters. Therefore, both are extremely accurate compared to one another. Moving on to vertical velocity, both graphs are clearly similar. Tracker says that vertical velocity is closest to 0 at t equals 0.96 seconds, while Desmos gives it at 0.94 seconds. Both times are extremely close, showing that they represent each other well. Here is vertical acceleration. It is clear that both graphs are reliably showing gravity, as both graphs are always negative, which is the direction of gravity. Desmos gives it as a definite constant, while Tracker has many more disparities in the data. However, that isn't to say it's not accurate at all. All of the data points seem to revolve around the value of negative 10, which is very close to Desmos's negative 10.5. Disparities like this can be attributed to shakes in the camera and the fact that a simple app is being used to record frame-by-frame data on a video from a phone, which is far from perfect. Here are the two representations of horizontal displacement. In keeping with Galileo's notion of constant acceleration for horizontal motion, the slope of both graphs are practically straight lines, with little hiccups in Tracker's data, which can be explained as before. However, both graphs are still nearly the same. They both go through 0 and exist in the range between 0 and 4.9 meters. Here are the graphs of horizontal velocity. This graph is perhaps the least reliable on trackers' behalf, most likely due to mistakes in recording and the spacing between the chosen frames of the ball in motion. However, all the data points seem to revolve around 2.5 meters, which is very close to Desmos's 2.6, making this a still reliable measure of horizontal velocity. And finally, here are the two graphs of horizontal acceleration. Just as Galileo proposed, it is clear that the acceleration in the horizontal direction is minimal, very close to 0. The manually derived equations give it as equal to 0 because that is how we started. Tracker clearly follows suit for the most part, with many of its data points lying on the x-axis of the graph, showing a value of acceleration that revolves around 0. That sums up my analysis of the flight of this ball while it's in motion. I use Tracker to identify and observe the quantitative data of its motion and use the data supplied to derive my own equations. By comparing the manually and automatically derived graphs, it is clear that both mirror each other very well, showing that deriving equations using calculus is extremely effective and can be used in the real world, minus a few disparities regarding air resistance and technological limitations and mistakes. Thank you for listening to my presentation.